Okay, well, thank you for the organizers for putting together this workshop. I think this intersection of UQ and data assimilation is indeed very fertile and very interesting. And so, word of warning, I'm sort of coming at this not from the perspective of a meteorologist or anyone who's terribly well versed in the application. I'm someone who does UQ, kind of coming at it from the applied math computational statistics perspective. But having looked at various issues in Bayesian inference and sort of computational statistics for many years and applying them to inverse problems, started getting very interested in questions of data assimilation, sort of taking inference methods that maybe we'd applied to static problems and bringing them to the dynamical setting, and the host of challenges that one faces, particularly when you want to quantify uncertainty, are very, very rich. So I'm excited to kind of talk a bit about that today. So the work I'm going to discuss today is joint work with my recently graduated PhD student, Alessio Spontini. And I'm going to talk about filters, nonlinear filters for some example systems that might be familiar to you, things like Lorentz systems, that are tied to the idea of couplings between probability distributions and transport. And I'll describe specifically what that means in a second. But just to kind of give a bit of perspective, so here's a picture borrowed from NCAR. What are the kind of problems that we're interested in solving? So, I mean, the introductory talk actually described many of these things. So here's a picture of a weather forecasting exercise. Problems that one might want to solve in this context are generally, say, state estimation. So you have a sequence of data arriving dynamically. You have a dynamical system that's evolving in time. And you'd like to estimate the state of nature, the state of reality, conditioned on the data that you have up until that time. And you'd like to do that in a recursive and online way. Because when you get a new piece of data, an hour from now, tomorrow, so on and so forth, you'd like to apply your algorithm in a way that whose cost doesn't grow with the whole sequence of data you've collected. You'd like to sort of have an online algorithm that's going to give you a new state estimate based on the new data that you've acquired. And you'd like to keep on doing this ad infinitum. And you might be interested in estimating the current state. You might be interested in estimating past states, given the data that you have. And maybe also you'd be interested in things like joint state and parameter estimation in a Bayesian setting. So maybe your dynamical system evolves in time. You'd like to estimate its state, but at the same time, there's some parameters describing the dynamics that are not evolving in time on the same time scale, and you'd like to estimate those as you acquire more and more data as well. So all these are problems of filtering or smoothing or joint state and parameter estimation that probably are familiar to many of you. Now, I'd like to solve these problems in a Bayesian setting. I'd like to cast them and solve them in a Bayesian setting, which means in some sense there are posterior distributions associated with each of these tasks, with filtering, smoothing, and joint state and parameter estimation. And our goal, computationally, is to characterize those posteriors, of course, subject to computational limitations, subject to things that we may or may not be able to access about the model, and subject to the desire to do this in an online and recursive way. So I can formalize it. I'll focus most of the talk actually just on the filtering problem. We can talk a little bit about smoothing and joint and state and parameter estimation at the end. But I'll formalize the problem as follows using this kind of graphical model. So you might consider this sort of simplistic, but this actually encapsulates the dynamical system and the observation system all in one. So here I'm using Z to denote the state of my system. So think of this as the state of my weather model. It could be very, very high dimensional. And I describe how the state evolves by discretizing time first and then writing a transition density. So the density of Zk, K is my time index, the density of the state Zk conditioned on the density on the state at some previous time. So essentially the dynamics are encoded in this transition density, pi of Zk conditioned on Zk minus 1. And then things that I might observe about the state are encoded in this likelihood. So this is really the probability density of the observations Yk, so the observations at the current time, conditioned on the state at the current time. So Yk conditioned on Zk. So graphically I represent that like this, where basically Z1 depends on Z0, and then the observations depend only on the state at the current time. So as I walk from left to right, I'm marching forward in time. I've discretized time. The states are the blue nodes, and the observations are the red nodes. Now, I might not observe at every single time, so some of these red nodes might be missing. I might observe only, a subset of the elements of the state. Z might be a big vector, and I might observe only a few pieces of it, or I might observe some funny nonlinear functional of the state. That's also possible. But all that can be encoded just by choice of these probability densities here. So having specified the model this way, let's say, okay, what are the kind of questions that we might want to answer? What are the posteriors that I described, that I mentioned in the previous slide, that we want to characterize? So perhaps the largest thing you could consider characterizing is the joint distribution of all of these states. So z from 0 to k, so I'm using kind of MATLAB notation here with the colon, so z from 0 to k, conditioned on all the data that I've observed. So this would be the smoothing distribution, and when I get a new piece of data, say little y k plus 1, I need to condition now, well, first of all, I have a new state associated with that. I have zk plus 1, and I have a new piece of data, but that new piece of data might actually tell me something about the state in the past. So it might actually carry information further back. And that's the nature of the smoothing problem. You're sort of conditioned on because I have new observations today, I could tell you something maybe more refined about what the weather was 6 hours ago. So this is sort of the largest problem, and this is a difficult problem in general. Well, A, because, well, it's sort of hard to do in one pass. You need to carry information backwards. And also, I mean, just written this way, this is actually a probability distribution whose dimension is growing in time. So first this is a k plus 1 dimensional distribution. Now this is a k plus 2 dimensional distribution. So it's growing in time. So one might be a little bit less ambitious and say, well, let's just focus on picking a particular marginal out of this joint distribution, and let that marginal be the marginal that represents the most recent state estimate. So this would be simply zk conditioned on y0 through k, and then when I get a new piece of data, when I'm now at time stage k plus 1, I want to look at zk plus 1 conditioned on all the data up until k plus 1. So that's essentially the most recent marginal, essentially saying, just give me the distribution of this state conditioned on all the data I've observed up until this point. Okay? It's the most recent marginal of the smoothing solution. Okay? Any questions on just this problem setup? So, yes. Yeah, and smoothing is going all the way back. Okay. So these are classical problems. They've been posed before, and sort of what are some common algorithms that people use for these things. I'm in no way doing justice to the whole variety of algorithms that people pose, but I'm just going to talk about two very broad categories. So one thing that people have often used for these kinds of problems are things like particle filters. And if you come from Bayesian computation, if you're a sequential Monte Carlo person, this is a very natural thing to do. I'll say in a second that these are, I would say, very, very difficult, maybe a little bit hopeless to apply to very large systems. But in any case, they have a lot of nice properties. So essentially, they say, I have this posterior, zk conditioned on y0 through k. So I'm just going to consider the filtering distribution for now. And I'm going to represent it with some samples. So these are samples centered at zk superscript I indexes the samples. And each sample will be associated with a weight. So all the samples don't have to have the same weight, but I'm just essentially going to approximate this filtering distribution with a collection of weighted samples. And what that means is when I want to compute an expectation with respect to this distribution, I just replace that expectation with a summation, in particular a weighted summation. Okay. So particle filters essentially say I have this batch of weighted samples, and I need to sort of let it proceed, let it evolve, let it sort of evolve as the dynamical system evolves and as I get more data. So particle filters are all basically how do I adapt this set of weighted samples as I get more and more, as I get more observations, as the dynamics push me into different places. And so this involves a bag of tricks that essentially combine things like importance sampling with resampling. Okay. Now, essentially then what you're doing is you're tracking this batch of weighted samples, and you hope that this batch of weighted samples represents the state as your system evolves in time. Okay. So on the one hand, these algorithms are very nice, because if I take more and more samples as n goes to infinity, I will actually characterize the Bayesian posterior. In other words, an expectation that I compute with respect to this, as n goes to infinity, I'll be able to tell you the true posterior expectation. And from the standpoint of uncertainty quantification, that is important, because, for instance, I might be interested in like the variance of this distribution. So I take the expectation of, say, z squared over this distribution, and then I'll get, some non-centered, and then I can subtract the mean. I can get the variance, or I can characterize the probability of some set, or I can do a lot of things just by being able to take expectations with respect to the target. So this is nice. This is a consistent algorithm from the UQ perspective. It sounds great. But what are the issues? Well, in general, so these particle filters can suffer from problems like particle degeneracy, and if you've played with these in practice, you certainly run into these. In other words, the weights might have a very large variance. You might have a bunch of particles with essentially zero weight. One particle might essentially contain all of the weight, in which case you could say the filter collapses. These issues are exacerbated by high parameter dimension, small noise, having many observations, a whole variety of things. it's not sort of as simple as a map from dimension to difficulty. There is kind of various notions of effective dimension out there in the literature. But a sort of rough takeaway of a lot of work that's been done recently by people like Bickel, Snyder, and Morzfeld is that the number of samples has to grow exponentially with this effective dimension of the system. And this effective dimension, as I said, depends on how big the system is, how much you observe, the noise in the system, things like that. There's a lot of interesting work nowadays about coming up with better proposals for the particle filters, putting the particles in a nice place. And in general, these can be successful, but they delay but do not sort of eliminate the collapse. So they can kind of defer the problem, but they don't really solve the problem. Okay? And one culprit, I mean, if you think about this, there's actually, I think, a fundamental reason that these things don't really eliminate the problem of degeneracy and collapse, is that what we're really asking for, okay, we're asking for a marginal of the smoothing distribution. And from the importance sampling perspective, we're proposing a bunch of particles and using importance sampling to represent this marginal. But we are not letting our proposal change on past states whenever we get more data. So in other words, think of this as a proposal distribution. We're asking for our proposal distribution to factor in this way. So I'm not really trying to just represent the current state. I'm trying to represent the state all the way going back in time. And the particle really has that meaning as representing a sample from the joint distribution. But I'm fixing sort of the previous k-1 steps and asking for only the k step to change, even though the data might really want the whole chain of particles to move. I can maybe describe that in a little bit more detail in the discussion session, but I think there's a fundamental reason that things like particle filters are going to run into trouble, because we want an online algorithm. We're limited in what we can do. Now, sort of the competing class of methods are things like the ensemble common filter. And I think mathematicians are kind of vexed by the ensemble common filter for a while, because it makes what one might perceive as strange assumptions, but in practice it works remarkably well. And remarkably well in what sense? In the sense that it can track the state pretty well. So, and I should say, ensemble common filter coupled with a whole variety of state-of-the-art and very problem-specific regularization techniques, tapering, inflation, blah, blah, can work quite well for complicated problems. But if I kind of idealize what the ensemble common filter does, it says, okay, suppose I have samples from the forecast distribution. So let me maybe take a step back. Say I began with the filtering distribution at the current time. I have samples that represent that filtering distribution. I apply the dynamics to those samples that carry them forward in time. And now I have samples from the forecast. So this is essentially the prior distribution, pi of zk plus 1, condition on y0 through k. This is the prior distribution for the inference step that will yield this posterior. So in going from here to here, what I'm doing is I'm conditioning on y sub k plus 1. That's the only change, and from this distribution to this. So here's the prior, here's the posterior. The ensemble common filter says, let me represent that change from prior to posterior using a linear map, using a linear transformation. Now that linear transformation is constructed from a Gaussian assumption, when in reality the problem is not Gaussian. I'll describe that visually in a second. But there's a Gaussian assumption plus various regularizing assumptions. But the nice thing about this is it actually moves samples into regions that are of interest. So there's this kind of contradiction. The problem is in general non-Gaussian. You derive this linear transformation based on some kind of Gaussian approximation, and then you apply it to a non-Gaussian ensemble, and you end up with another non-Gaussian ensemble, and you proceed. Okay. So so here's a very simple example, and this is not my slide. I borrowed this from Chris Snyder at NCAR, but this is actually one of the nicest illustrations that I've seen of what happened, the difference between the particle filter and the ensemble common filter. So here, suppose I have, this is my prior distribution. This is my forecast ensemble. This is samples from pi of zk plus 1 conditioned on y 0 through k. So this is samples from this guy over here. Okay. I have the black are samples, and then the blue lines are actual contours of the density. So here, this is a simple problem. We can write it down analytically where I just presume to know everything. And I'm going to tell you it's just as though the blue is the real prior, and the black are samples from the prior. If I apply a particle filter, what happens? Okay, so I'm not telling you what the observation are. The observation is essentially that x1 is somewhere around here, somewhere in the vicinity of 1 to 1.5, observed directly with some Gaussian noise. So it's actually saying, look, state, you should condition on the fact that you're sort of in this vertical slice. And what does the particle filter do? Well, it takes the samples that are in that region of high likelihood, it gives them high weight. And the samples that are far away from that region, it gives them low weight. It did not move the particles at all. So you may not be able to see this actually so well in the slide, but basically the circles here appear where there were black dots before. Okay? So particles are in place, they just get new weights. Okay? This is the most vanilla particle filter you could imagine. There are better particle filters that might try to put the particles somewhere else, but this is the simplest one. But on the other hand, I mean, what is the posterior? So the gray are the contours of the true posterior, and it's nice and bimodal, and indeed the particles represent that bimodality. But you can also see you've left a bunch of particles behind. These particles have become kind of useless for the purpose of computing the expectation. But here they are. So I'm representing the posterior. If I iterate this long enough, though, I'm going to get into trouble. This is the sort of one, that's the failing of the particle filter. Now, what does the ENKF do? Begin the same forecast ensemble, makes a Gaussian approximation of this, even though this is a non-Gaussian distribution, derives an update rule from that Gaussian approximation. Turns out to be a linear transformation of the particles, essentially. And I apply that linear transformation to the particles, and the particles end up as the blue dots over here.